I like to be able to just read. It requires less mental capacity.
Yes, that's right. Thank you for thinking that I needed that, because I did. Okay. 1:31. So I'm going to go ahead and get started. Thank you all for coming today. We are honored to have Glen Romine from NCAR as our seminar speaker today. Glen is a research scientist, as I said, from NCAR. His interests include prediction and predictability of high-impact convective weather, ensemble data assimilation, observation impact, verification, diagnosis of model bias, and regional ensemble analysis and forecast system design. Just a few interests. And that's, those are just things that are included here. There are probably others. In the past few years, he and his team have been collaborating with the HER development group to aid in the efforts of that group to move from a deterministic to an ensemble prediction system. And today he'll be sharing select activities in this area with his presentation titled Convection Permitting Ensemble Design Strategies in a UFS-Style Framework. Thanks for being here, Glen.
Thanks, Jack. All right, thanks for coming. It's a pleasure to be here and to have an opportunity to share some of the work we've been doing. I understand Craig Schwartz gave you guys some ideas on some of the ensemble analysis and activities that we've been working on back in, I think, November. So this will be some of the other activities that we're working on as well from the team. So I realize you guys all know this, but I think it helps to share with you that I guess this is my view of what I think I know of what you guys are trying to accomplish, and that is moving towards this sort of unified forecast system where you would really have a shared modeling environment. So you really don't want to have all these conglomerates of systems anymore because they're difficult to maintain, and so you want to move to a single system, which, from a theoretical perspective, sounds fantastic because it gives you the opportunity to then share components, especially physics, because from our view anyway, physics is extremely important, and moving towards a coupled modeling framework, maybe for weather prediction, the value there will take a little longer to fully mature, but certainly as you go out into longer predictions, it's critical. Of course, making all these changes is painful, particularly when you're talking about forklifting a lot of different components in. So when you start changing the model, the physics, and soon the DA system, this basically breaks everything every time you want to change a component out, and there's very little institutional inertia and knowledge of how these systems are going to interact with each other. And that, from a development standpoint, is pretty painful and difficult. And right now, we basically don't have the tools in place to be able to understand what's going to break as soon as we start swapping these pieces out. And yet the pathway is pretty clear, particularly for the part that we've been most involved in, particularly working with Jacob and then the group from, I guess it's GSL now, on the HER development, moving towards an ensemble framework that someday will be called this Rapid Refresh Forecast System, is the current acronym of choice. But that's going to be envisioned as having a single dynamic core and a single physics suite. And that's a hard pathway from where we're at right now. So if you look at what the current operational ensemble prediction system is, it's an ad hoc conglomerate in the HREF system that really is just taking a bunch of deterministic forecasts, well, not a bunch, but 4, maybe it's 5 eventually, but 4 right now deterministic forecast systems, 2 where you have time lagged, some are old, some are new, and then you generate some guidance from it, which produces a lot of spread, but is very difficult as a system to make it better because you have all these individual components. So how are we going to move forward on this? So you really want to represent the fact that there's uncertainty in physical processes, and that's a known thing. And when you put all these different multi-physics, multi-model pieces together, that can help cover some of the parameter space. And so that's a piece that we're going to have to overcome in going to a single physics suite. And we really want to improve the forecast reliability so that we're missing fewer of these sort of bad forecast events. But really, this multi-model system is kind of is the starting point, and it's going to be difficult to basically replace. So the pathway that I guess we're trying to suggest is not new. It's basically trying to follow the pathway that's been done at the European Center. And that basically is that when you move to this single modeling system, that you really just have to commit to it, go all in, and then have a very systematic approach for how you make improvements to the system. And so that's a pathway that we're starting to try to implement in our own experimental development, and that we're hoping will be of value to others. And so ultimately also when you have spread developing within the system, you would like that to be flow dependent. So when the spread gets large, it tells you that you're in a weather pattern that has low predictability, as opposed to just telling you that you have diverse physics, and those diverse physics lead to different outcomes. It's not what you're necessarily looking for. So I'm going to first talk about a way to improve the mean forecast analysis skill through a formal method as opposed to doing it in an ad hoc method. And the most straightforward way of doing that is actually taking advantage of a system that we already do right away. So when we do data assimilation, we're routinely confronting the model with observations. And often they don't agree particularly well, particularly in a systematic sense in various ways. And that systematic model error is something that we can directly go after in terms of trying to improve our forecast systems. And so our main goal here is to basically develop a systematic approach for moving forward on this. And so we're going to use a method that was first demonstrated back in 1992 by Klinker and Sardavuk, where they basically used what's known as a mean initial tendency method, or mean initial tendency averaging. I've seen it referred to both ways. But basically, you put this approach within a continuous cycle data assimilation system, and it's a way to find model errors and then attribute them to specific physics errors. And so I'll go back to their paper here just to give an example of sort of how this might work. And so if you look at the bottom panel there, that is forecast errors, where they've basically looked at a long time period comparing their analysis to their forecasts, and they can basically find that there's a specific pattern, in this case near the top of the boundary layer, where there's errors in the forecast system. And then in the top panel is where they basically done a budget on the momentum, and that same pattern is pretty clearly evident. And so the basic idea here is that maybe now we can use this averaging tool to be able to, one, find patterns that match the errors in our forecast systems, and then once we found them, can we then start to improve them? And that was further demonstrated in some work by Rodwell and Palmer. And so in the upper left panel, they basically are running a forecast system so that the different lines are vertical profiles from different dynamics and physics tendencies within the system. And so average over a long period of time. And then the heavy dashed line in black that runs through the middle is the bias of the total system. And then the heavy red line that's close to the middle is averaging all those tendencies components together. So you can see a lot of the tendencies from different components tend to oppose each other and balance out to be close to zero. But in the left case, you can see between, say, 353 and 202 hectopascals that there's sort of the dipole feature in the systematic bias. So that's the feature that they're trying to address. And then in the far right in each of the panels is the cloud fraction vertical profile. And so they had a suspicion that basically they had an excessive amount of clouds present and near the tropopause. And so in the upper right is when they basically address that, reduce the amount of cloudiness. So you can see the cloud fraction goes down. And now the bias looks a lot better. And then to just demonstrate how physical processes can basically provide a clear signal for errors, they took the entrainment within the system in the bottom two panels. And on the left and the bottom panel, they divided the entrainment by 5, so basically you end up with undiluted parcels ascending in the convective scheme. And so the convective scheme is shown there at the blue profile, and you can see that leads to a marked increase in the heating rate from the convective scheme, particularly as you get up into the upper troposphere, and then it leads to quite a bit of moisture transport that leads to a great deal of cloudiness that severely affects the bias. Whereas on the right, the entrainment is markedly increased, and so that lowers the heating profile because now you're diluting your updrafts considerably, and so most of your heating ends up being in the lower troposphere, and again you end up with a significant systematic bias in the system. So in these ways, you can play around with changing different physics components and basically see how it affects not only that specific component, but how it also interacts with the other physics. And this is the advantage to this approach. So I mentioned before the importance of doing this in a cycle data simulation, and the reason for that is because we really want to just have the interaction in this tendencies be between the observations and our modeling system. If we use partial cycling, such as what is used in the current HER data simulation system, we throw away that information and we're introducing another source of bias that is coming from the large-scale modeling systems that we're injecting into it. And so it's not just between this modeling system and the observations. So we want to try to keep that clear. And really, the data simulation systems were not designed, or not theoretically designed anyway, to cope with systematic errors. We really just want to be correcting random errors. And we don't want it to have to do much. We'd like that background to be as good as possible. And there's been numerous studies that have shown that the more you improve the forecast model used in your cycle data simulation system, that it has a tremendous positive benefit on the analysis skill and subsequent forecasts. Okay, but if you start looking at averaging these model analysis increments over long periods of time, it proves that this can be a challenging problem to go after when you're looking to fix a systematic bias. So in this case, just to demonstrate this, these are seasonal biases in 2-meter temperature. So it's going from the winter season, December, January, February in the upper left, to fall, September, October, November in the lower right. And what you can see is that spatially there's quite a bit of variability, and then there's seasonal variability in systematic biases that exist within the system. And so you always have to be very careful when you decide that you're going to go after a bias that it's a representative time and that you know specifically what you're going after, because otherwise you could make an improvement based on one season's outcomes and find yourself making things much worse in another season. And so always helpful to look at a long period of record in these. And then even if you look across the diurnal cycle, you'll find quite a bit of variability in the mean updates done by the system. So this is just looking from 6 UTC, 12, 18, and 0 UTC. And so the patterns change quite a bit over the day, and this is also owing to the fact that the observing network is changing over the day. So for instance, we only have radiosonde observations at 12 and 0 UTC, and then our ACARS observations, we see a lot of them that show up in the early morning hours on the East Coast, and then they march towards the West Coast. So there's a lot of changes in the observing network that makes this, again, messy and a bit challenging. And even if you look in a vertical profile, so now again, the color profiles are mean analysis increments in temperature, and then zonal wind on the right at different times of day are the different colors, and then the black is the sort of average over the day. And even there, you see quite a bit of variability from different times, and the patterns look different based on the variable you're looking at. So it is a bit squirrely to chase after these things, and we're just going to try to fix the big mean black line first, and then we'll worry about the diurnal parts later. I guess that's the best we know what to do right now. So, all right. So again, going back to this idea of how are we going to disaggregate these components. So I don't know if this mouse does work. So let's assume, for instance, that this orange line here is sort of observations marching along forward in time, okay? And then each one of these little hiccups here is when we're doing an analysis. and then the green lines that are marching away from the observations is our model. And so before we were looking at an average of all these little increments. So if we just take those and time average them over a long period of time, and then we can spatially plot them out. But now what we want to do is actually extract out diagnostics during the forecast integration to be able to get the tendencies for each of the individual components. And then we can disaggregate those into these individual physical and dynamical processes to be able to see what is going on during these model integrations that's making our model want to not look like the observed world. All right, so we're going to keep life simple initially as opposed to trying to chase down a random error. We're going to do something more like the Rodwell and Palmer study, and we're going to just change something that we know just to see if we can address something. So in this case, the black line here is the diurnal cycle of precipitation in a 48-hour forecast averaged over a lot of forecasts from MRMS. And then the blue line is with the TICA cumulus parameterization. That's from the Zhang et al. 2010. And then there's a change in the CAPE closure scheme that was suggested by Bechtold et al. And that this is what's used in the current EC system. And so if you look at the diurnal cycle in the blue, the original system, you can see that the peak in precipitation occurs basically when the sun angle is directly overhead, is when the convection all triggers. So it triggers too early in the day, and then by 24 hours, when we might, say, be making our zero UTC analysis and forecast, you can see that we're past the peak in the diurnal cycle when we should be at the peak in the diurnal cycle. And so it seems like this would be a potential source of error in our analysis system, and so let's try to fix it. And so we go to the new closure scheme. They're shown in red, and that delays when convection occurs within the system, and we get a better agreement with the diurnal cycle. Notably, there's a big peak that's excessive, and we'll come back to that. All right, so again, we can do something like we saw before. We can start breaking apart those vertical profiles of tendencies into different components. And not surprisingly, one of the ones that changes the most is the cumulus heating. So we have temperatures in the top row and then moisture in the bottom row. And while we are mainly targeting the cumulus scheme, we actually end up with reactions from all the other schemes as well. And so even though we've only changed one, all the others react to the change in the climatology caused by the tendencies that come out of that particular scheme. But what's most notable with this change in the triggering is that because we're delaying convective initiation, CAPE builds up to larger values, and so our heating profile is deeper when we go to the new TICA scheme relative to what we had before. And so we see big changes in heating in the upper troposphere. Another feature that comes out is that we saw quite a bit of change in the moisture profile. And in this case, it's basically leading to less mixing because the shallow scheme turns out to be far less active with the new TICA. More of it's going into the deep convective, and the shallow scheme is far less active. And so when we look at overall changes from this, just looking at how the bias was affected by this change in the trigger scheme, things looked a lot better in the mid-troposphere by making this change. However, in the boundary layer, we actually made things worse. And so that was a question of like, well, did we make the right move by changing the scheme because we made part of it better and part of it worse? So this is where that sort of physical intuition part often comes into these processes. So what we ended up having to do was going back and looking at the climatology of shallow clouds to try to figure out whether the shallow scheme was being less active in the new scheme was more close to correct. And so we did that, and in fact, that is what we found, is that it should be less active. And so then we had to go back and say, well, why now do we have so much moisture accumulating in the boundary layer? And what we came to the conclusion of was that it was actually a problem with the land surface model. So we're using the RUC land surface model in this scheme, which is what's typically used in the HER. And when we switched to the NOAA MP model, that's the bias profile shown in green here, you can see basically our moisture bias goes away completely. And it also markedly improved in the lower right here that overproduction of rainfall during the peak in the diurnal cycle. And so we viewed this as a win, That said, it did then change the temperature profile, and so we ended up with going from a small negative bias to now a small positive bias in temperature. So like anything, you hit one mole, another one pops up somewhere else. So it's a never-ending process, but I think you can see how this provides you a pathway towards how you might do that process and how you can see when you make changes how it's affecting other physics. Because sometimes, in this case, if we'd have simply retracted our initial change, what it was doing actually was the overactive shallow scheme was hiding an excess moisture bias here by transporting it into the mid-troposphere and making it go away so it didn't look so bad. And so these things require time and patience to track down, but it is a pathway. All right, so I'd also like to talk a little bit about ensemble reliability. I think there's still quite a bit of uncertainty in this area of trying to decide, when we look at ensemble dispersion, how important are the characteristics of our initial perturbations and how quickly does the error grow. And so we're going to basically step through a very simplified approach to see how this works. So the basic idea here of, I mentioned before that we're interested in sort of spread that's reflective of the characteristics of the flow pattern. This is sort of a classic study by Palmer in '93 where he looked at the Lorenz attractor. So in the left panel here, basically this is a highly predictable regime where you could pick perturbation members from out of this side of the attractor, and as it flows to the other attractor, the envelope of solution stays pretty close together. So you can think of this as weather forecasting when there's not much convection going on. So we're pretty good at it when the dynamics are dry. Life is easy. And then on the right is basically when you go into one of these potential regime changes where the forecast is very sensitive to the initial conditions. And this is what we would like our forecast systems to do, to have spread that's representative of how predictable the atmosphere is about to be. And what usually kills us is these regime changes. And there's been some recent studies, so I really like this. There's a series of papers. I'm pointing out one in particular from Baumgart, but they've done a few pretty interesting papers lately on this idea of trying to figure out how error growth occurs within the system and how it grows upscale. And so in this particular case, I think they're using the Plant and Craig cumulus scheme. So this is, again, at large-scale models. But they're starting off with errors that get introduced through the cumulus scheme. And what they've shown here is basically different error growth rates based on processes within the system. And so the sort of physics processes are down here, and then this expands into more of the dynamical processes that goes through this stages of error growth over here on the left. And so what they basically demonstrate is that the physical processes are dominating the short-term predictability, but then they quickly saturate, and there's not much more you can do by continuing to perturb those. It then becomes, once these diabatic events occur, you get a big outflow basically against the dynamic tropopause, and then that changes the dynamic predictability of the balance flow. And then that finally grows up to the baroclinic instability, which is a slower growth rate. And then finally you get up to Rossby wave packets. And so kind of going through this progression would give you some idea. For instance, if I really wanted to go in, if I'm looking at a particular window of time that I'm trying to improve the predictability, this kind of provides you with a roadmap of where I should be looking for adding more perturbations to get error growth at that time, because if I just put it into one place, it's not necessarily going to be effective after a certain period of time. Okay. And then another study that Mark Rodwell did. Mark Rodwell does a lot of my favorite work. He's like one of my personal heroes out there. He was looking at basically forecast busts in Europe, because of course they're interested in Europe weather, not just because they're there. I think that always helps. Even though they do global prediction. But they were looking at how sensitive forecast busts were to just changes in initial perturbations. And in this case, this is an initial perturbation applied to improve this really bad forecast. So the scale here is quite large. It goes from minus 360 to 440 meter height forecasts at 500 millibars. And so this was a big bust in Europe. But they could put some tiny initial perturbations in, and then voila, they get a far better forecast. And so it gives you so much sense that sometimes this is, I guess, what you might call a low predictability event. And so with some small initial perturbations, you can capture an event that wasn't likely to occur. But more often, what tends to come up is just complete dropouts. So there's some recent work by Claudio Sanchez that's been looking at this, but it's part of the NAUDEX campaign, where they're looking at, for instance, exotropical transition, getting caught up into the waveguide, and for a long time, the forecast systems just can't capture that interaction. And so as you look out, the forecast errors are just enormous, right up until you get within about 72 hours, and then finally the modeling system can latch onto that. But prior to that, the RMS errors are very large and the spread is quite small, and it just isn't capturing the range of possibilities out there. Okay. And I will throw in a caveat before I go too far of that sometimes we worry about spread, and maybe we shouldn't. So this is from a survey we did. So some of you may know we ran an experimental forecast system for about 2.5 years. And at the end of that, we sought some community input. And surprisingly, even though we knew that our system was statistically under-dispersive, forecasters thought that it was just about right. So I think sometimes they just put a lens on it. They don't expect everything to actually be in exactly the right place. And so I'll throw that out as a caveat of, like, we should probably focus on improving the model mean trajectory before we worry about the spread too much. But let's see what we can do with perturbations and how much they matter.
Wait a minute. You're saying that the forecasters prefer a less accurate forecast?
Well, I'm saying that the forecasters maybe aren't as worried about having a statistically reliable forecast system as model developers are.
Around here, they're always worried about what they call a flip-flop. You know, when the model does 6 hours or 12 hours or 24 hours apart, it makes two different forecasts. You know, and that drives them crazy. And they'd like to know if that's going to happen, and of course, they'd like to know which one is better.
Yeah, I'll leave that to you guys. So let's consider some different perturbation characteristics. So that shown here in the fills is basically time average spread, and then the mean height contours of 700 millibars are shown. The main point being that there's some flow-dependent perturbations that are provided by a formal ensemble data assimilation system here on the left. This is from the SREF, and so this is what was done at NSSL for a few years in generating their ensemble forecast systems, is they just pulled perturbations from the SREF system at 3-hour forecasts and then initialized forecasts based on that. And then on the right would just be from random covariance. This is drawn from the WRF-DA tool, so it's basically just the NMC method for coming up with correlations, and then you put random perturbations in and do draws from that. So you end up with a very uniform perturbations that have nothing to do with the flow of the day. Okay, so if you look at vertical profiles of those, so this is zonal, meridional wind, temperature, and then water vapor perturbation climatologies from these 3 different sources. And the main thing you can note is that the flow-dependent perturbations do a lot better at capturing where the spread should be near the tropopause. The random perturbations aren't so great. And then within temperature perturbations, there's not great structure, again, for these random perturbations. They're perhaps larger than you might prefer as you get into the upper troposphere. And they also have the largest low-level moisture perturbations. But this is what we get from drawing them out of the system, and they're cheap and easy. And if it doesn't matter, then let's just use those for our forecast because they're easy. So let's first try to look at this from a spectral perspective. So here, larger wavelengths are going towards the right. The total kinetic energy at 200 hectopascals is given in the solid lines, and then the perturbation energy is given in the dash. So the main thing to note here is that so this is our random perturbations. They have relatively low overall energy because they're nice and smooth, and we've tuned them to have a peak energy that's around 400 kilometers, and so there's basically no small scale energy that comes out of these whatsoever. Meanwhile, our DART ensemble analysis, which is done at 15 kilometers, has the most total energy at all scales just because it's a finer scale analysis than what we're starting with on the other two, which are sitting on top of a GFS. And then these perturbations have a lot of small-scale energy, but not a lot of larger-scale energy relative to, say, the Schreff, which has the most large-scale energy. And so if we just take these and then integrate forward in 12 hours, how do things change? One thing, it doesn't seem to be particularly valuable to have that small-scale energy because it saturates out and goes away. And now, despite the fact that this random perturbations seem to have the smallest initial energy, they end up with having the largest perturbation energy by 12 hours. So what does that end up doing to things? Actually, there's one other thing I wanted to point out here. So the Schreff, while it starts off with this large-scale, bigger perturbation energy, a lot of that is coming from the fact that it's drawn from a multitude of different systems. So these are domain total precip, and then the color coding here basically tells you what the initial core was that those perturbations were drawn from. And you can see that there's residual information based on those different initial conditions and physics within those members of the Schreff that persists mostly through the next diurnal cycle, but somewhat also all the way to the end. So that's part of where the spread comes from in that system. So forecast skill, how much does this matter for forecast skill? So shown here are a bunch of little squiggly lines. The most important thing is to note is that this is a fraction skill score for changing precipitation thresholds, so going from very light to approaching convective rainfall. What's probably most obvious is that the skill decreases as we go to higher rain rates because we're just not as good at forecasting high-impact weather. And then the flow-dependent perturbations are in the black and the blue. And so the black here is from the Schreff perturbation skill, and so higher values are better. So the Schreff seems to provide, perturbations initially provide more skillful forecasts. And then the random perturbations do actually degrade the forecast skill by not being flow-dependent. So in some ways, perturbations do sort of matter for skill. The more important thing here is given by the dashed lines, and this is if we use a less skillful mean analysis. And so the less skillful mean analysis is by far the bigger factor, and so improve the mean if you want to improve your skill. Improving perturbations can also improve your skill, but it's not super important what those perturbations look like as long as they're flow dependent. And we can look at this in reliability diagrams as well. Again, you want to lie along this diagonal for good reliability. And as we're moving from left to right, we're going to higher rain rates. And so as we get to higher rain rates, we don't have very reliable forecasts. So we may have high values of agreement within the ensemble on where extreme precip is going to occur, but it's usually wrong. So, but as we get to lower rain rates, we have better skill. And if anything, we're perhaps over-dispersive with the random perturbations in the short term. If we go to the next day predictability, all the systems tend to lean more towards the still being under-dispersive, and so we're still not getting enough error growth at those large scales just based on our initial perturbations. So we can look at this in a variety of different ways. So one of the tools that was suggested by Sercel et al. Was to look at this thing called the power ratio. And so it's basically if you take an individual member and you just start progressively smoothing it to larger scales, at what point can you no longer discriminate it from the ensemble mean? And that gives you a number as to what scale that occurs at. And when you can't discriminate from the ensemble mean, you basically saturate at this power ratio of 1. And so based on these different perturbations, one thing that you can see pretty quickly is that the warped DA perturbations, these random perturbations, very quickly saturate and then stop growing. And so we're not seeing a continual progression. Whereas the flow-dependent ones, perhaps we're tapping into that baroclinic instability component that we talked about before. You see that there's a continuous march to grow spread to progressively larger scales, which is what we would like to see. And we can start to look at these spectrally as well and break them down by spatial scale to look at errors and spread on for each of these different spatial scale components. And so the color coding here is basically by spatial scale. So as we go from the warm colors, we're near the grid scale, and then as we go towards gray, we're basically up to domain scale. And so first off, that this is a mean squared error on the left, and then ensemble variance on the right. And then the different line patterns are based on the different perturbation sources. So one thing you might note right away is that the mean squared error isn't particularly sensitive to what our perturbation source is. So that's, I guess, good. And then as you move towards the variance, you can see that it is fairly sensitive, but it depends on what scale you're looking at. So for instance, as you go to smaller scales, basically the variance disappears quicker. So it saturates at small scales, works its way up, similar to what we saw from the power ratio. But there are certain scales where the perturbations still matter even out to 48 hours. And so we're still getting some impact in certain scales. Another thing you can see here, for instance, is that there's a definite diurnal cycle. The errors tend to grow at small scales first, grow upscale, and then decline to progressively larger scales through the diurnal cycle, which is probably just from upscale growth of convection into organized systems. But the general truth here that's perhaps hard to grasp is that the variance is just, again, no matter what the scale, it's generally smaller than what you would like it to be. And so that's maybe easier to see if we look at it just in terms of spread scale ratio. And so these are across the different systems. So with random perturbations, we get this gigantic overshoot at all scales, and then it settles down and basically stops growing. The flow-dependent perturbations tend to have a more consistent pattern of growth at all scales, but you can definitely see that the Schreff perturbations are growing a little bit faster than what we're getting from the DART initial conditions. We can also look at this in other different ways. So we could first just go to the surface and try looking at the surface energy norm. And so we're going to stick back to that initial scale that we mentioned before at 256 kilometers, because we could see in that precipitation anyway that was one where the perturbations persisted. And here we're basically dividing it into different components. So blues in wind, temperatures are red, water vapor green, and then surface pressure is in black. And then the total of all those combined is this set of black up here. You can't even see the pressure because it basically is not normalized, and so it ends up looking really small. So this is mean squared error on the left and then variance on the right. And again, you can see that the mean squared error is not particularly sensitive, regardless of what perturbation source we use. Whereas in spread, there's definitely a notable residual that persists throughout. And we are seeing that the rate of variance is growing, and if we compare the rate of the mean squared error and the rate of growth of variance, they actually are about at the same rate. It's just we're starting off with way too small a value. So it's just that our initial analysis is far too confident relative to the actual mean squared error. But the growth rate actually looks about right. And so it gives us some hope that with a better initial analysis perturbation scale that these would look more favorable. All right, so just in summary, the process, I guess, that we think has potential value is really looking at these initial tendency methods. It provides you with a formal approach to trying to attack errors in the forecast system. Unfortunately, our current paradigm is basically that we rely on physics experts to find errors, and they're really good at knowing what knobs they can turn that can fix a given error. The problem is they usually do it without consultation to anyone else, and two people might be trying to fix the same error, and then you mash them all back together again, and then you end up with something that's much more difficult to interpret because too many knobs have been turned simultaneously. So I guess we're suggesting that that's maybe not the best way going forward. And then for initial perturbations, I guess the biggest take-home is that the mean analysis quality is a first-order thing to worry about. But perturbations do matter, but the most important part is that they're flow-dependent. Maybe not the details of how they're flow-dependent is most important. But we do hope to be able to take advantage of using these types of tools, for instance, when applying stochastic methods to improve ensemble dispersion, to be a little bit more targeted in how we do that. So instead of just going after it randomly, to go after it with a very specific purpose. And so those are things that we'll be continuing to work on. So we're right now building these tools into the HER v4 framework with expectation of using that as a baseline, so that then when we switch to the FE3, we'll have the exact same tendency diagnostics to compare to, and we'll be able to identify how similar those same physics behave in a different dynamic core, where there will now be different dynamic tendencies that will get thrown in on top of it. So it's a way to basically have a more controlled understanding of what's going to change when you start switching in the different pieces. And then all these tools that we're working on building to look at ensemble variance and the initial tendency method, we're going to be putting into the MET+ system, along with documentation to allow people to use them and test them and hopefully find them helpful in their own model system development activities. And with that, I'll close.
Thank you. Questions?
In the tendency part, what do you do about the spin-up? In the first 3-6 hours, there's a lot of balance. Are you just seeing that? How do you put that away and look at something a little cleaner?
So the hope there would be that your forecasts are basically running at the same resolution in your analysis system. And so this is kind of viewed from, you would do an analysis at the same native grid and then forecast on that same native grid. And that way there's basically no spin up associated with changing the grid resolution. But then you will have some initial imbalance that comes through, but that usually goes away after just a few time steps. So we've usually found that if you wait 30 minutes into the integration, that those initial errors tend to damp down, and then you can move forward. 30 minutes, yeah. It's pretty quick. The main things are, for instance, if you look at the new TICA scheme, it now takes other tendencies as inputs to that scheme, and those initial tendencies don't get updated very often. So for instance, you tend not to call radiation very often, and so you get this initial tendency from the first call to radiation, but then it doesn't get updated again for quite a while, and that very first call is usually not very good in terms of the tendencies that come out with it, and then you're stuck with them for a while. And so you kind of want to wait for those types of things to settle down. But yeah, usually after a couple of calls to the radiation scheme, those look pretty good, and the rest of it was pretty stable in our tests anyway.
So are those accumulated tendencies? I mean, back presentation is like accumulated over time.
Yes, so we would run these over, just for our initial testing, we usually looked at about a 30 to 45 day period where we would average all of these. And so we would do 4 analyses per day over a, I think, 35 day period for the results I showed here.
Okay, so the tendencies are accumulated every time step, right?
Right. Okay. Yeah, you sample the tendencies every time step at every grid point. And then you can average them out how you want. So the profiles I showed here was averaged over a central U.S. region, just to make it more tractable. So in the stuff that Mark Rodwell did, they, for instance, were interested in tropical convection in a particular region where they knew they had bad forecasts, and so they just picked a spatial region over the tropics out of the global system to look at, to attack a specific problem. I think you probably have ideas of similar difficult areas to forecast that you could focus in on, that you may want to try to look at what's going on in the physics and why they're not behaving the way you would like them to.
Other questions? I guess I have one. So you definitely pretty emphatically cautioned against changing more than one thing at a time. We have a real challenge here at EMC in that we're on tight time deadlines, and we often do change more than one thing at a time when we're doing our testing, especially in crunch time to ready to get an implementation, because we just don't have the cycles. We can't run 45 days at every season with one change at a time. are we, I guess, how badly are we, I mean, I know that intuitively you shouldn't do this, especially with nonlinear systems, but how can we minimize the impact of compensating, of introducing compensating errors with with the time constraints that we typically have? Do you have any suggestions for that?
So we did build a testing framework where we basically were able to fix all the tendencies except for the one that we were trying to work at, just to try to understand, and then we could basically run a single time step and then see how sensitive the system was going to be to that change. And so in that way you could probably do some very preliminary testing of multiple things to find out whether it's likely to really upset the balance before you then ran an extended period with numerous changes. So I think it's definitely doable with a little creativity. So you'd have to run it initially to come up with a baseline, and then in a testing framework you could definitely try these things out. So we'd be happy to help someone out if they wanted to try that.
Yeah, I mean, that would be great, because we are currently working with the DTC to develop a single column model with saved tendencies, so that we can essentially duplicate in a single column mode whatever solution we're getting in the 3D model. So all the effective tendencies and everything are saved, so that we can systematically do that sort of thing.
So we basically built one too, I guess. So.
Okay. Well, I know this is part of the problem. That's why we're doing community modeling, right? So I was just going to say, maybe we can get you trained in that
sure.
with the DTC. But if you've already got one built, yeah, I should probably have Grant Furl. I don't know if you know Grant, but talk to you about.
No, we've been working with Tara on our transition tools, but yeah, I don't know Grant.
Okay.
Question. So once you know the tendency, say for short wave and non-short wave and hitting non fully, but you don't know which one is the truth. Is the short wave hitting too large or non-fully too large? You still need some kind of observation. The baseline to compare, right? You cannot totally rely just the tendency diagnostics.
I agree completely. I think, it does require a lot of, physics intuition to know what the likely problems are, but then you do need to go back to observations to try to fill in the gaps. So for instance, when we ran into that initial problem with the boundary layer being too moist, and we were trying to figure out, well, was this a problem with the physics scheme, or was it or were we actually making it worse by what we were changing? And so we basically went back and did a cloud climatology of deep and shallow clouds and counted the occurrences of them, and then compared that to the climatology of the deep and shallow triggering of convection within the cumulus scheme to be able to figure out which one was right. And so we couldn't have done that without observations as a grounding framework. And so observations are always your ground. It's just they're not always easy to figure out how they impact, how they disagree with the model in systematic ways. Where's the physical processes that are causing that disagreement? And that's more what we're trying to suggest, is that this provides you an initial framework for doing that in a more systematic way as opposed to doing it completely ad hoc.
I have another question. So you rely on the analysis increments, so the layer how good or bad the forecast is. But usually in the cycle data simulation system, there's another knobs you can kill. You can make the analysis increments larger and smaller, right? So based on the analysis system, so sometimes we hide the actually problem by we can reduce the increments from the observation side.
So, there's a lot of challenges, I think, in that aspect, just because, as you say, like the analysis increments are basically the only thing that you're using to to draw the modeling system back towards the observations. And it's not complete. It doesn't get you all the way back there. But that's basically just suggests that you have to be very careful in where you try to make changes, that you need to be in a place that's well observed. So there was another study by my buddy Mark Rodwell. I think it's in the 2018 paper that was in BAMS, but yeah, he was talking about how you can really take those analysis increments and you can break them down based on how confident you are in what's driving them, and you can look at the value of the observations that you have to compare against. So for instance, if you're in a place that's completely satellite observation bound, you just don't have a lot of confidence in those particular observations, versus in other areas where you maybe have lots of redundant observations that help compensate for some of the systematic biases within the observing networks, and then you can be more confident about the misfits in those places and make changes there. But it's all challenging, but I think that there are some tools that are out there for how to approach these problems.
So for a model, you'd recommend that we distribute all tendencies out into like experimental development model, not the operational ones, it would take too long to write them out.
Yeah.
But we would maintain all the tendencies and maintain structures that we could write out every time step. Is that what you're thinking?
Well, I think that an initial implementation you probably would need to make some choices. So initial ideas that I would have would be, let's grid it first before, put it on a really coarse grid, because you probably don't need full grid structure for this information. But you could grid it within the model and output it on a very simplified grid to make it more manageable. We usually integrate the tendencies over longer periods of time. So for instance, we'll integrate them over a full hour to get a sample. And so you really are only outputting a single profile of data, basically, out of the system for every time you run it. But in an experimental DA system, it doesn't add a lot to the cycles necessarily. Well, we've only done this in WRF and MPAS. We haven't done it yet in FE3. We're not anticipating in FE3 that it ends up being computationally a big drag, but it will be a computational drag, and it does take time to output fields. So you definitely wouldn't want it in an operational framework. But I do think if you were really going through a cycle where you were trying to test a bunch of physics improvements, that it would make sense to try applying it and seeing whether it helps you understand what you're going to change when you implement those new physics.
It's almost what we do now, but not for everything.
Yeah, sure.
Other questions in the room?
There are quite a few people on the line.
Questions online?
13 people.
Okay. Last call. All right. I guess we're done. Let's thank Glenn again.